All right, folks, Fast Action is back in action here. On this page of notes, we are actually going to jump into solving our logarithmic equations. If you have not watched the video on the previous page of how to condense logarithms, you need to go back and do that because that is going to be a crucial skill in solving most of our equations here. So, types of logarithmic equations primarily fall into these two categories, although there are some exceptions. So for our logarithmic equations, what we are going to need to do to solve it is rewrite, just like we did with our exponentials. We're going to need to rewrite and or possibly condense, okay? So oftentimes you will need to condense these so that the equation will meet one of these two requirements. Now, not every logarithmic equation will fall into these two categories. There are a couple fairly uncommon exceptions that we will see, and we'll discuss those in class. So the first one is if we can get the log equation, the log equation to equal just a number, or if we can get a single logarithm on each side. Now, in order to get a single logarithm on each side, we are going to need to make sure that the bases match. If the bases don't match, it does not fall into this particular category. That's really our special exception. So we're going to make sure that the bases match, and then the two arguments will equal each other. So that was one of our properties that's listed on the top of the previous video. The other thing that is really important that's different than our exponentials is that we do need to remember that we cannot evaluate logs that are 0 or logs that are negative, okay? So we want to keep that in mind. Remember, exponentials, we didn't have that concern, but our logarithms, we will. So let's jump into our problem here. And when I look at my first one, what I want to keep in mind is this logarithmic piece needs to be isolated before I can do any other analysis. So that's our rewrite portion. So I'm going to move that 23 to the other side. So I'm going to have log base x of 64 equals a 2. Now, I've mentioned this a couple times. You can kind of draw in this line here just to help you just check, make sure that your notation is good. These should all look like the same font size and just the x is the subscript. Now, I have log equal to a number, so I can switch this to its exponential form since those are inverses. So I'm going to switch this to my exponential here, and I'm going to have x squared equals 64. Solving this algebraically, I would take the square root of each side. So I would get x equals plus or minus 8. However, I only want to have my positive base, so my final answer is actually just x equals 8. Don't assume that the negative is always rejected because it is not always going to be rejected. Next one, I need to isolate this piece before I can do anything else, and I do have two options. I could technically take this 30 and I could write it up top as an exponent, but that'd be a pretty big exponent for me to have to deal with. And what I can see is this 60 is easily divisible by 30, so that's going to be my easier strategy on this problem. So I'm going to have a log base 3 of 4x minus 7 equals 2. Now I can switch to my exponential form because I have log equals a number. So I'm going to have 3 squared equals my 4x minus 7. So I have 3 squared equals 4x minus 7. Of course, 3 squared is 9. 4x minus 7, just do some basic algebra 1 work here. So I'll have my 16 equals my 4x, and x equals 4. So when I look at this 4, I need to make sure that this 4 is going to keep this argument positive. 16 minus 7 is positive, so sure enough, that's just fine. My next example, just moving on, I have my logarithm and I have a logarithm, but this coefficient of a 2 is causing a problem here. So this coefficient of a 2 right here, I could always, like I did on the previous problem, try to divide it on both sides, but it's not going to help me. It's just going to give me a denominator over here. So I'm going to write that one up top as an exponent this time. You really just need to practice these and figure out what's going to work best on each problem. So I'm going to have a log base 5. Sorry about that there. Got a little ahead of myself. So I'm going to have my log base 5 of x squared equals my log base 5 of 9. Now I can see that I have log base 5 on each side, so these arguments must equal each other. So I'm going to have an x squared equals 9. I'm going to take my square root of each side. So I'm going to get an x plus or minus 3. Then I'm going to go ahead and I'm going to check, does both the positive and the negative work? And I look at this log right here and I say, no, I can't have the log of that negative 3. So my final answer is just going to be x equals positive 3. Again, I'm going to say it. Don't assume that the negative gets rejected because it does not always get rejected. Next, when I look at this problem, I've got several things going on. I have a log and I have a log and then I have this constant. If I didn't have this constant and I just had the two logs, it would be a pretty simple problem. So what I'm going to do on this problem is I'm going to take this logarithm here and I'm going to move it to my left-hand side. So I'm going to have my log base 5 of my x plus 6, and I'm going to add to that my log base 5 of my x plus 2, and that's going to equal my 1. Now I still have a little more work to do, but using my condensing properties, since these two logs have the same base, I can condense those together. So I'm going to have log base 5, and I'm going to have my x plus 6 times my x plus 2, and that's going to equal 1. Now I have a log equal to a number, so I can switch that to its exponential form. So I can have 5 to the first power equals that product. So I'll have 5 to the first, and I'm going to go ahead and I'm going to expand that out. So I'm going to have an x squared plus an 8x plus a 12. I can see I've got a quadratic here, so I'm going to move everything to the right-hand side. I'm going to have an x squared plus an 8x plus my 7. This is going to nicely factor. So I'm going to have my x plus 7 and my x plus 1. Solving this, I get x equals a negative 7 and a negative 1. So let's check and see. Do either of these work? X is negative 7. If I put that into this first log, I can see it fails. So I'm going to immediately mark that one out. X is negative 1. If I put it into this first log, negative 1 plus 6, that checks out. Negative 1 plus 2, that also checks out. So here's a good example where a negative number still worked as a solution. One more example on this page. This one I don't really have to do any moving around, but I do need to condense these two logs. Notice that yes, the bases match. That is a crucial element. So those bases match, we're going to condense these. This time my logs are being subtracted. So when I condense this, I'm going to write this as a log base 2, and I'm going to have 5 divided by x plus 7 equals 4. Now I can switch to my exponential form. So I'm going to have 2 to the 4th power equals 5 over x plus 7. So I'm going to have 16 equals 5 over x plus 7. I always think that it's easy to take that left side and put it over 1, so it's a little easier to see that we're just going to cross multiply this proportion. When I cross multiply that, I'm going to get a 16x plus my 16 times 7 is going to give me 112 equals 5. Solving this, I'm going to get my 16x equals my negative 107. So x is a negative 107 divided by 16. If I want to approximate that as a decimal, I certainly can do that. And a negative 6.6875, that is kind of a useful thing to do in this case, because if we want to check whether this value is acceptable for a logarithm, the decimal is going to be easier to work with. So a log of a negative 6.68, when I plug it in to this logarithm right here, I see that it checks out just fine. So this final answer is also okay, even though it's a negative. So that's all that we have. And again, we will look at the special case of what to do when the bases don't match in class.